Hello folks, this is Doug, and in this video I'm going to talk about how you make epoxides. There's two main ways that we're going to discuss. I want to show them both to you and we'll do a few examples. So one way is from the halohydron. You might remember that these are made from alkenes usually. So from alkenes. I'm not going to review how to make halohydrons very much at all. I'm just going to assume that you already know how to make them. But the idea, right, is that this X is any halogen, so this is some halogen. And if you take a halohydron and you add some sort of base, and it can be any base you really want, usually smaller bases are used, but it could be really anything. The idea is that you can make that into an epoxide, and I'll show you the mechanism in a second. The second method is that you can use any peroxyacid, and there are some that are more commonly used, like MCPBA, which we'll talk about in a second. But if you look at this, they're talking about an acid like a carboxylic acid. Right, normally a carboxylic acid would be C-double-bond-O-O-H. So that'd be your normal carboxylic acid. Since this is a peroxyacid, so peroxyacid, the idea is that, right, remember that per means an extra oxygen. So per means an extra oxygen, like perchlorate, peroxide. An extra oxygen, so the peroxyacids look like this. So a peroxyacid looks a lot like a carboxylic acid, only instead of being C-double-bond-O-OH, it's C-double-bond-O, carbon with a C-double-bond-O, an O, and an extra O, and an H. So you have an extra oxygen here, hence the per. So it's a peroxyacid. So the second way to make epoxides is you take an alkene, add a peroxyacid, and that also makes the epoxide. So let's take a look at some of these in a little more detail, right? These are the two main types. So first, the halohydron. Here's a specific one, right? I've got my alcohol, I've got my bromine. They're on adjacent carbons. They're vicinal, hence the halohydron. And in this case, specifically, I have sodium hydroxide. So the idea here is that if you have a base like sodium hydroxide, one thing you want to keep in mind is that because it's basic, it can do acid-base reactions. And acid-base reactions are super, super quick. They're very quick. They're one of the fastest types of reactions that you're going to see. They're way faster than most organic reactions. So you might think that this hydroxide can do one of two things, right? One, maybe it can do a backside attack on the bromine and then do a SN2 type reaction, and then you'll get your diol. The other thing, though, is that it could act as an acid. So you kind of are balancing the two of those. Or sorry, that it could act as a base. You're trying to balance those two. If it acts as a base, it plucks off this hydrogen, which leaves the O minus. So this would be a reversible step. So you have your Br. You have your O minus, you just made water. And this is reversible, right? O minus here versus O minus there are pretty much on par, ignoring any small inductive effects. They're more or less the same pKa's, they're within like 1 or 2. So this is fairly 50-50-ish. The interesting thing, though, is that once you have this O minus on this molecule with the bromine, what happens is it can do basically an intramolecular SN2, where this oxygen can basically just lean over and attack this carbon with the bromine on it to give you your epoxide. So now that oxygen sort of leaned over, kicked out that bromide to do what we would refer to as an intramolecular SN2. So this would be an intramolecular, let me erase that, intramolecular SN2 type reaction. An SN2 type reaction, right? Because it kind of does a backside attack. It's one step. It doesn't involve a carbocation or anything like that. And that's the mechanism, right, for these reactions. So here's your mechanism. How we can form an epoxide from a halohydron. And it's that same mechanism basically done over and over again. For any halohydron, it doesn't matter if it changes to iodine or chlorine. You'll have an OH on them anyways, and so it's just the same mechanism. Your base, whatever the base is, takes off the hydrogen on the alcohol, then you have the alkoxide, and it just leans over and kicks out whatever leaving group is there. So you might see them directly, like where you start from the halohydron, or you might start from an alkene and make your halohydron. So in this case, in step 1 stuff, right, I have iodine and water, so I can make a halohydron out of that. So now I have iodine and water. If making halohydrons and all the rules for halohydrons are unfamiliar to you, then I would definitely recommend you look in your book. I'm not going to talk about it in this video. We're focusing on making epoxides. So step 1 would make your halohydron. And then step 2 stuff, right? In step 2, I just have sodium hydroxide again. And again, that's going to remove this H so that you get your epoxide right here, right? So again, where this oxygen right here basically ended up attacking where the iodine was to make your epoxide, your 3-membered ring, your highly energetic intermediate, or not intermediate, your highly energetic product. And so that's all you have to worry about that one, right? So I took in this case, I made the halohydron, and then I added a base, got my product, got my epoxide. And same thing in this case, this one, I just want to show you one with a cyclic one, or one that might have some stereochemistry. Again, if you remember back to making halohydrons, which is probably back with alkene stuff, my bromine is going to be added first, so that's going to go on the bottom face. And then my water, just because for steric reasons, right, I've got this bridge on top, so the bromine is going to add on the bottom face, which means my water has to attack on the top face, so I get my OH up there. And then in my second step, right, it's the same thing. Second step, in this case, I have methoxide and instead of hydroxide. It doesn't matter what the base is, just that it's a strong base. So then your methoxide will take the H off of this O, and again, this O is going to lean over to attack that carbon where the bromine is, and so your product will end up looking something like this, where you have an epoxide on the top face of your bicyclic compound here. And so that would be your product there, whether you have an epoxide on top. And so those are some examples, right? Here are 2 more examples of making an epoxide from a halohydron. You just need to add a small base, basically. That's the idea. We'll talk more about what types of reactions epoxides do in the following videos. So here we have a peroxyacid, right? So the peroxyacid method. So here's CF3CO3H. So this molecule would look something like CF3, C double bond O, 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 H. And what I'm going to do is I'm going to try to show you this mechanism here. I'm going to kind of realign this so that it looks a little bit differently. So if you take your alkene, and I'm going to draw my peroxyacid like this, kind of got to get it in the arrangement I want. And I'm drawing it like this because probably it looks like this a lot of the time. It depends on what the solvent is, but you might expect some hydrogen bonding between those two. And what we're going to see here is that this peroxyacid is going to donate one of its oxygens to the alkene. And it's a weird mechanism. There's some electrocyclic stuff going on. You have electrons both going to and from an oxygen. But let's just kind of take a look at how this is all going to play out. Like I said, this carbonyl oxygen is going to be attracted to this hydrogen, right? Just normal hydrogen bonding. The oxygen is partially negative, the hydrogen is partially positive. So these 2 pi electrons are actually going to go right here to form a new OH bond, is the idea, a new OH bond. And since you're making a new bond to this hydrogen, these electrons from this hydrogen, they need to go somewhere, they need to break off, is the idea. They need to break off. And what happens is that those electrons end up going to that alkene. Those electrons are going to go to that alkene. But the alkene can't have all those electrons. It also needs to spit electrons up, and so it's going to spit electrons up onto that oxygen from which those electrons came. And that's going to be the oxygen, this one, I'll even draw it in green here. That's going to be the oxygen that ends up in your epoxide. But oxygen can't have all of those, right? We got this really weak peroxide bond. Those electrons are going to drop back down to form a carbonyl. And so it's really, really weird. For my students, I'm probably not going to ask you how to draw this mechanism because it's just not super intuitive at all. And I'm not sure there's a lot of good learning that can go on here. So double bond O, CF3, and then like I said, that green oxygen is here now, and that's what became part of my epoxide. So then I've made my epoxide product. Right, here we go. So what would I write over here as my products? I'd say, okay, well that turned into this. I got my epoxide, and now I have CF3CO2H. So basically it transferred the oxygen from the peroxyacid to the alkene to make the epoxide. The peroxyacid turned into regular carboxylic acid is the idea. That's your mechanism. Again, for my students, I don't really care that you memorize this one so much, but I want to show it to you just so you have some vague sense of what's going on here. Here's our mechanism. I have a couple of examples down here. A very, very common peroxyacid that's used for these types of reactions, especially in like textbooks and stuff, is called MCPBA. That stands for metachloroperoxybenzoic acid, and it looks like this. So meta probably means nothing to you yet if you haven't done aromatic nomenclature yet, but meta means that it's two away from some group. So metachloro is MC, and then PBA is peroxybenzoic acid. So peroxybenzoic acid. This is MCPBA. So meta chloro peroxy benzoic acid. And the most important thing here, right, is that it's a peroxyacid again, right? That's if you react a peroxyacid with an alkene, you're gonna form an epoxide. So all I need to really do right here is just find where I have my alkene, and instead of having that alkene there, just draw the epoxide. So just draw a 3-membered ring with an oxygen coming off of it, your oxirane. Your oxocyclopropane. That's it. Same thing down here. I have MCPBA again, and I have that same compound that I had before with the bicyclic compound with the alkene. But it's going to be the same thing, only now, since the oxygen comes from just one molecule in this case, the peroxyacid, that molecule is probably going to approach from the bottom face, so it can stay away from this bridge. And you're going to end up where your epoxide is actually on the bottom side of this. So here's my bridge, it's on top, and my peroxide probably is going to be on the lower part in this case, so it'll be on the bottom. Here's a couple more examples. So if there is some stereochemistry to worry about, in this case, just put the peroxide on the other face, the face that's less sterically hindered, and you're going to be fine. You'll notice that on this bottom example, using MCPBA, using a peroxyacid, the epoxide's on the bottom face, and if you flip back in the video to the previous slide, when we use the halohydron, the epoxide's actually on the top face. So you can actually kind of control, do you want the epoxide on the top face or the bottom face, depending on which method you use to make your epoxide. So hopefully at the end of this video, right, you're more familiar with the two ways that we can make epoxides. One is through the halohydron, one is through the peroxyacid. In the following videos, I'll talk about now what do we do with these epoxides? How do we open them under basic conditions? How do we open them under acidic conditions? And how are they similar and how are they different? So if you have any questions or comments, please leave them down below. Happy studying.